All right. Welcome to another deep dive.
Yeah.
Where we grab some recent research and unpack it for you.
Right.
So today we're going to look at a preprint from March 2025. And this one is about large language models.
Right.
You've probably heard of these LLMs.
It's big ones, yeah.
And this research looks at how they handle word sense disambiguation.
That's right.
WSD.
Yeah, word sense disambiguation, or WSD for short.
Okay.
It's a really fundamental problem in computational linguistics.
And, I think a lot of our listeners are probably familiar with LLMs, but maybe not so much with WSD.
Right, yeah.
So could you break down what exactly word sense disambiguation is?
Yeah, so basically, think about this, right?
Okay.
A single word can have all these different meanings.
Oh, yeah, for sure.
And WSD is all about figuring out which meaning is the right one.
Okay.
Based on how that word's being used.
Based on the context.
Yeah, exactly.
Yeah.
So, take the word bank. If someone says they went to the bank, do they mean the place where you keep your money?
Right.
Or the side of a river?
Yeah, two completely different meanings.
Totally, yeah.
That makes sense. So that's the kind of ambiguity that we're talking about here.
That's exactly it.
Okay. And I imagine this has been a really tough problem in NLP for a long time, right?
Oh, yeah. For a long time, getting computers to do WSD accurately was just a huge challenge. And there have been all sorts of different approaches over the years. Yeah,
so we've got these super powerful LLMs now.
Right.
And it seems like they just get language. They're doing all these incredible things.
Yeah.
So it makes you wonder, are those older, more specialized methods? Are they even still needed?
Right.
You know?
Do we even need WSD anymore?
Exactly.
Can these LLMs just figure it all out themselves? And that's what this research really digs into.
Okay, cool. So let's jump into that. What did they find out?
So one of the big takeaways is that when you just use these LLMs straight out of the box, without any specific training for WSD.
So this is zero-shot learning.
Yeah, exactly. Zero shot.
Okay.
They actually do pretty well.
They do.
Yeah, they can often get the right meaning of a word just from looking at the words around it.
Okay.
But here's the thing.
What's that?
They don't immediately beat those specialized WSD methods.
Oh, interesting.
Yeah, those methods that have been refined for years and years.
Okay, so it's not like just having a huge model automatically solves this problem.
No, not quite, no.
Okay, interesting.
But here's where it gets even more interesting.
Right, listening.
They took a smaller LLM.
Okay.
And they did this thing called fine-tuning.
Fine-tuning?
Yeah, basically they trained it specifically on WSD data.
Okay.
And guess what happened?
I don't know what.
This smaller model,
yeah,
after it was fine-tuned, it actually ended up doing better.
Better?
Yeah, better than all the other models.
Wow.
Including the state-of-the-art WSD systems.
So even better than the big, huge LLMs?
Yeah. Well, it was specifically trained for this.
Oh, that makes sense.
Yeah.
Wow, that's a really cool finding.
Yeah, it is.
It kind of shows that, even with all this general knowledge that these massive models have, if you really want to get the best performance for a specific task, you still got to do that targeted training.
Absolutely. That targeted training is key.
Really interesting. Okay, so to test these LLMs on WSD, they built on this existing benchmark, right?
Right. So there's this benchmark called XLWSD.
XLWSD.
Yeah.
And they expanded it, right?
Exactly.
To make sure they were really testing how well the models understood the meanings of words in different contexts.
They needed ways to really probe the LLM's understanding.
Okay, so what do these new evaluation methods actually look like?
Okay, so they came up with two main types of tasks.
Two types.
Okay. First one was all about definition generation.
Definition generation.
Yeah, so they would give the LLM a sentence with a specific word. And they'd ask it, okay, what's a short definition of this word as it's being used in this sentence?
Okay, so they have to come up with their own definition.
Exactly, yeah.
Based on the surrounding words.
Yeah, and if the same word showed up more than once in the sentence, they would specify which one they meant.
Okay, so the first bank or the second bank?
Exactly, just to make sure it was super clear.
That makes sense.
Yeah, no room for ambiguity in the prompt itself.
Right.
And then the second type of task was multiple choice.
Multiple choice, okay.
So they'd give the LLM a sentence with the target word and then a list of possible meanings.
Right.
One of them would be the right one, according to XLWSD.
Okay.
And the others would be wrong, but still kind of plausible meanings.
Okay, so they're trying to trick it a little bit.
Yeah, a little bit.
Got
Just to see if it could really pick out the right one.
Right. Make sure it's not just guessing.
Exactly.
So one task is about explaining the meaning, and the other is about recognizing the correct meaning.
Yeah, that's a good way to put it.
Okay. And they did all this in multiple languages, right?
Yes. So they used this benchmark, XLWSD, which is already multilingual.
Oh, okay.
And they paired it with BabelNet.
BabelNet.
Which is this massive network of words and their meanings.
Okay.
Across tons of languages.
So they were testing in like 5 languages, you said?
Yeah, English, Spanish, French, Italian, and German.
Wow, that's pretty comprehensive.
It is, yeah.
Okay, and they were also like careful about handling the definitions across those different languages, right?
Yeah, so BabelNet has these definitions, these glosses.
Glosses, okay.
But not every meaning in every language actually has an original gloss.
Okay.
They also looked at what happens when you use machine translations.
Machine translations.
Yeah, to fill in those missing glosses.
Okay, so they wanted to see if that affected the results.
Exactly.
Okay, so that gives us a good idea of like how they set up this whole research study.
Yeah, it does.
But to really appreciate what they did, I think it'd be helpful to like take a step back.
Yeah.
And look at the history of WSD.
Right, a little historical context.
Yeah, how have people tackled this problem over the years?
So like the very early attempts at WSD, they relied on what we called rule-based system.
Rule-based, okay.
Yeah, so imagine you have all these rules.
Okay.
Like, if this word is near these other words, then it probably has this meaning.
Wow. Okay.
Very explicit, very handcrafted.
Sounds like it would take a lot of work.
Oh, yeah, a lot of manual effort to create all those rules. And then, along came knowledge-based approaches, which started using those sense inventories we talked about.
Like dictionaries and WordNet.
Yeah, dictionaries, WordNet, BabelNet. And these systems tried to look at the relationships between words in a sentence and then compare those to the different meanings in the inventory.
Okay, so using that structured knowledge to figure it out.
Exactly.
Gotcha.
And then as we got more and more digital text.
More digital text?
Yeah, like huge collections of text called corpora.
Corpora.
And more computing power.
Right.
Supervised learning became a big thing.
Okay.
Which basically means you train a machine learning model on a bunch of text where humans have labeled each word with its correct meaning.
Okay, so you're showing the computer tons of examples.
Yeah, tons of examples.
And it learns from those.
Yeah, but that meant someone had to label all that data.
Oh, wow. That sounds pretty time consuming.
Oh, it was incredibly time consuming and labor intensive.
Wow, okay, so the internet came along, gave us even more text data.
Tons of it.
And things like knowledge graphs.
Yeah.
And those really helped those supervised and knowledge-based methods.
Yes, exactly.
Okay.
And then in the late 2010s,
we saw these transformer-based language models emerge.
Okay.
With BERT being a really big one.
BERT. Yeah, I've heard of BERT.
Yeah, BERT was a game changer.
Okay.
Because it could understand the context of a word in a much deeper way.
Okay.
It could create these really rich representations of words, like vectors that captured their meaning in that specific context.
Okay, so that led to a lot of progress in WSD.
Yeah, people started fine-tuning BERT and others similar models for WSD.
Gotcha. So these earlier transformers were already pretty good at understanding the surrounding words to figure out the meaning.
Exactly.
And then we have these LLMs now.
Right.
And their ability to do all these tasks without specific training.
In that zero-shot way.
Zero shot, yeah.
It suggests that they just have this really deep understanding of language built in.
Okay.
So it's natural to ask, do we even need dedicated WSD techniques anymore?
Right. That's a good question.
And that's what this research really gets at.
By evaluating these newer LLMs in a zero-shot setting, but also by looking at how they do when they're fine-tuned for WSD.
Right, which is something that hasn't been explored as much before.
Exactly.
Okay, so that history lesson was really helpful.
Glad it was useful.
I think it really gives us a better understanding of where this research fits in the grand scheme of things.
For sure.
So let's dive back into the specifics of this study.
All right.
Can you walk us through how they actually tested these LLMs?
Yeah. So the first step was creating their benchmark.
Benchmark creation.
Right. So to evaluate WSD, you need a collection of text where the right meaning of each word has been identified.
Okay.
That's a sense-annotated corpus.
Right.
And you also need a list of all the possible meanings, which is a sense inventory. Gotcha. Yeah. So they went with XLWSD as their corpus.
Okay.
And BabelNet as their inventory.
So they had their testing ground and this set of possible answers.
Yeah, that's a good way to put it.
Okay. And then they had to figure out how to ask the LLMs to do the task.
Right.
So for definition generation, what did those prompts look like?
So the prompts basically said, like, here's a sentence. Give this short definition of this word in the sentence.
Gotcha.
And if the same word appeared multiple times, they would specify which one they meant.
Right, like the first bank or the second bank.
Exactly.
Okay, and for multiple choice?
So for multiple choice, they gave the sentence with the target word.
Okay.
And then a list of possible meanings. One was the correct one from XLWSD.
Right.
And the others were incorrect, but still plausible meanings from BabelNet.
So try and make sure it's really understanding the nuances.
Exactly.
Yeah.
And they also made sure to only use instances where the word actually had more than one meaning in BabelNet.
Right, otherwise it wouldn't be a real test.
Exactly, yeah.
Okay, and they did this all in multiple languages.
Yes, so they made 2 versions of the benchmark.
2 versions, okay.
One with only instances where BabelNet had original definitions, those glosses, for all 5 languages, and another version where they used machine translations to fill in the gaps.
Okay, that makes sense.
Yeah, so they could have a bigger data set.
And then they divided that data into training and testing sets.
Exactly.
Okay, so that's their benchmark creation.
Yeah,
Sounds like they put a lot of effort into making sure it was comprehensive.
They did, yeah, a really robust setup.
Okay, so what did they do once they had this benchmark?
So the next part was their methodology.
Methodology.
Yeah, which involved 2 main approaches.
2 approaches. Okay.
One was zero shot.
Zero shot, okay.
And the other was fine-tuning.
Fine-tuning, okay.
Yeah, so for zero shot, they just gave the prompts directly to several different LLMs.
Okay, so just seeing how they perform out of the box.
Exactly.
With no specific training.
Right.
Okay, and what kind of LLMs did they use?
So they used a bunch of different ones, including different versions of Llama 3.1.
Llama, okay.
Mistral, Gemma, and Qwen 2.
Oh, okay. Good mix of popular models.
Yeah, and they used a cloud service to run them.
Okay.
And a method called greedy search.
Greedy search, what's that?
So greedy search means the LLM always picks the most likely next word.
Okay.
When it's generating its response.
Ah, okay.
So it's a pretty straightforward approach.
Gotcha. Then for fine-tuning.
So for fine-tuning, they took one specific LLM, Llama 3.1, with 8 billion parameters.
Okay, why that one?
They chose it because it was good at multiple languages.
Ah, good multilingual capabilities.
Right, and they trained it specifically on their WSD benchmark data.
Okay, so they basically showed it lots of examples of words in context.
Exactly, tons of examples.
Along with their correct meanings.
Yeah.
So it could learn the patterns.
Exactly.
Okay, and then they had to evaluate how well the models did.
Right, the evaluation.
Okay.
So for definition generation, they used 2 metrics.
Yeah, okay.
One was Rugel, which measures how similar the words in the generated definition are to the words in the correct definition.
Gotcha.
And the other was BERT score.
BERT score.
Which looks at the meaning.
Okay.
So does the generated definition actually capture the same meaning, even if it uses different words?
Okay, so looking at both the words and the underlying meaning.
Exactly.
And for multiple choice, it was just accuracy, right?
Yeah, just straight up accuracy.
How often did they pick the right meaning?
Exactly.
Okay, and they had different evaluation scenarios, right?
Yeah, depending on whether they used original or machine translated glosses.
Okay, makes sense. So what were the big findings?
All right, so for the zero shot evaluation.
Zero shot, okay.
They found that in general, bigger LLMs did better.
Okay. Size matters.
To some extent, yeah.
Well, but it wasn't the only factor.
Right.
Okay.
So Gemma 2.9b was really good at the multiple choice task across all the languages when they only used original glosses. The bigger Llama 3.1 models did better at definition generation.
Interesting.
And there wasn't a huge difference between the 70 billion parameter Llama model and the much larger 405 billion one.
Oh, wow. So diminishing returns there.
Yeah, it seems like Qwen 2 was really good for Spanish and French.
Interesting.
And they found that using machine translation for the glosses seemed to hurt performance a bit.
Okay, so sticking with original definitions is probably better in a zero-shot setting.
Yeah, it seems like it.
What about when they fine-tuned the Llama model?
So fine-tuning that Llama 3.1 model led to big improvements.
Big improvements.
Yeah, across all the languages and all the metrics.
Wow.
And generally, the more training data they used, the better the accuracy.
So more data, better results?
Pretty much, yeah.
Okay.
The machine-translated data during fine-tuning didn't really affect things when they tested on the original glosses. But when they tested on the translated test set, the performance seemed to be affected by the bigger data set size. And maybe the fact that there were more complex cases of polysemy.
Right, words with lots of different meanings.
Exactly.
Okay, so how did this fine-tuned model compare to those, like existing best WSD systems?
That's a really important point.
That don't use these huge LLMs.
Right.
Like, what happened there?
So their fine-tuned Llama model actually outperformed the previous best systems.
Wow, really?
Yeah, it got really impressive scores, especially for English.
So that suggests that fine-tuning a smaller LLM can be a really effective approach for WSD.
Absolutely.
Okay, and the zero-shot LLMs, they didn't consistently beat those baselines.
No, they didn't.
Interesting. Okay, so what are the real-world implications of all this?
Okay, so there are a few key takeaways.
Okay.
First, it shows that even though LLMs have all this general knowledge, task-specific fine-tuning is still the way to go.
Okay.
If you want the best possible performance on something like WSD.
Right, you got to specialize.
Yeah. Okay. The fact that the 8 billion parameter Llama model did so well after fine-tuning is also important because it means you don't necessarily need the absolute biggest models.
Right, which can be a real pain to work with.
Oh, yeah. They're super resource intensive.
Okay.
Second, better WSD could lead to improvements in all sorts of other NLP applications.
Okay, like what?
Like, think about search engines, machine translation, text summarization.
Okay.
All those things rely on understanding the meaning of words.
Right.
So more accurate WSD could make them work a lot better.
That makes sense.
And then finally, the fact that the researchers made their benchmark and their fine-tuned models public is really great for the NLP community.
Yeah.
It'll help other people build on their work.
So it's not just about the findings, but also about the tools they've created.
Exactly.
Awesome. Okay, well, now it's time for our Novel Notions segment.
All right, let's get creative.
Yeah, so based on this research, what are some interesting future research directions?
Okay, so here's one.
Okay.
What about using LLMs to create sense inventories?
Ah, okay, to actually build those dictionaries.
Yeah. So we've seen that these fine-tuned LLMs are good at generating definitions.
Right.
What if we use that ability to, expand BabbleNet?
Okay, interesting.
So we could give the LLM a word in lots of different contexts.
Okay.
And it would generate a definition for each one. And then we could analyze those definitions.
Okay.
Look for patterns, differences in meaning.
Yeah.
And maybe even come up with new senses that aren't in BabbleNet yet.
Oh, wow. So the LLM is like a constantly evolving dictionary.
Exactly.
That's really cool.
Yeah, I think it could be a really fruitful area of research.
Okay, what else?
Here's another one.
Okay.
Personalized word sense disambiguation.
Personalized.
Yeah. So we all have our own ways of using language.
Right. Our own little quirks.
Exactly.
Okay.
So a general WSD model might not always understand those.
Yeah, that makes sense.
So what if we fine-tuned models on an individual's own writing?
Okay. So train a model on my emails and documents.
Yeah, something like that.
Okay. But how would you even get that data?
Well, a lot of people generate a ton of digital text. Emails, documents, social media posts.
Okay.
Obviously, you'd have to be careful about privacy.
Right, correct.
But that could be a really rich data set.
Okay.
And then you could fine-tune an LLM on that.
So it learns how I specifically use language.
Exactly.
And then that model would be better at understanding my writing.
Exactly. It would be personalized.
That's a really cool idea.
Yeah, it could lead to some really interesting applications.
Okay, those are some really great ideas.
Thanks.
I love that, that idea of using the LLMs to improve the very tools we use for WSD.
Yeah, that's a cool twist.
Yeah, and that personalized WSD, super interesting.
It'd be really neat to see where that goes.
Okay, so to wrap things up, what's the big takeaway for our listeners?
I think the biggest thing to remember is that fine-tuned medium-sized LLMs are currently the best we have for word sense disambiguation.
Okay.
They even beat the huge general purpose models on this task.
So even with all their knowledge, they still need that specific training.
Exactly.
Really interesting stuff.
It is, yeah.
It makes you think about the balance between general intelligence and specialized expertise.
Absolutely.
And how that applies to AI.
Yeah, it's a fascinating question.
Okay, well, for those who want to dive deeper, we've got a link to the paper down below.
Check it out.
Thanks for joining us for this deep dive.
Thanks for having me.
And we'll leave you with this thought.
Okay.
As AI keeps getting better at understanding language, what other problems that we thought were solved might see some surprising breakthroughs by combining these massive models with really targeted training.
It's an exciting time for NLP.
It really is.